Hi everyone, my name's Leanne. I am the Quality Assurance Lead at East Kent Hospitals in the Pharmacy Department. I'm going to be talking to you today about microbiological monitoring of our clean room. To give a bit of background by this point, we know that to make aseptically prepared products, we work in a controlled environment called the clean room. As its namesake suggests, we want to be keeping that environment clean, specifically from microorganisms, as these can lead to product spoilage, but even more detrimentally can cause harm to an immunocompromised patient by causing illness. So a bit of background about myself. I started my career in microbiology in a quality control lab. I've had the benefit of working in many different companies for many different types of industry. So I've worked in the pharmaceutical industry, I've worked in the cosmetic manufacturing industry, I've worked in fertility, and now I am in healthcare. So I have a wide knowledge base of microbiology for varying types of products, and although the application is different in each type of industry, the principle is the same. We are trying to maintain a high quality product that is free from microbial contamination. So the first thing we need to consider is why. Why do we monitor? When we are making products in a clean room, we need to consider what we are trying to achieve. So eventually what we are looking for is a product that is fit for purpose and only contains the necessary constituents. Therefore, we want it free from all contamination. Contamination can be in various forms. We have solid matter contamination or particulates. This is known as non-viable contamination as it's not living. Examples of this can be things like dust or soil from outside. We also have chemical contamination, and that can come from things such as cleaning agents, so the residue from cleaning, or spillages from other products, piercing vials from aerosols, and aerosols from cleaning fluid also. And obviously what this section is about, microbial contamination, so the viable organisms that can proliferate. And this is what we're focusing on today. Think about your surroundings in an aseptic production unit. What could introduce contamination? So unfortunately this isn't an interactive chat. We can't have this chat in person, but so I'm going to run through a couple of things. So obviously you have your surrounding environment itself, the airflow, the quality of the air outside of the unit. You have the transfer of equipment and product and consumables into your clean room that can carry contamination in, and most importantly, the personnel, so people. We are the biggest contaminant of a clean room, therefore we carry in lots of viable organisms and particulates. Here is a list of references I would urge you to go away and research and review for your own benefit. They will provide a lot more detail surrounding this topic than I can give in my space today, but they are really good resources to have a look at, and it's what we base all our guidance on and our SOPs and our processes. So the sterility assurance and competency of personnel. Aseptic processing has a sterility assurance level of 10 to the negative 3 compared to 10 to the negative 6 for terminally sterilised products. So a sterility assurance level is a term used in microbiology to describe the probability of a single unit being non-sterile after it has been subjected to the sterilisation process. Obviously, in an aseptic production unit, there is no terminal sterilisation. We have to have assurance that final product is fit for purpose. So can we be certain that no contamination has been introduced during manufacture in our aseptic production units? The answer is no, we can't. The reason being is we cannot test each end product, especially in section 10 units. That product is a patient specific product, and the entire amount needs to be administered to the patient. We cannot take samples and we cannot make extra samples for testing. We have to build assurance into the process as we cannot test the final product. We rely on the environment, the operators and the equipment to give us that assurance, to make sure we have a high quality process that leads to a high quality product. Okay, so what do we monitor? We have many things in the clean room that we have to monitor, and it's not just all about microbiology. We monitor the environment, so the clean room itself, the facility. We do microbiological monitoring, and this is by a number of means that I'm going to discuss in a bit. One of the reasons we do micro monitoring is for cleaning efficacy. So essentially we are reviewing regularly the process of cleaning and making sure it's maintained to a standard that microbes are not able to proliferate. We're also looking at the performance of the air handling unit when we're doing microbiological monitoring, because we want to make sure that our air handling unit is performing to a level that it is reducing the risk of microbiological proliferation in our clean room. To support the microbiological monitoring, we also do a lot of physical monitoring. So this is really important. It's not direct microbiological monitoring, but it really supports the understanding of our local microbiological flora. So physical monitoring includes things such as the pressure differentials between rooms, the air flows, the air change rates, and particulates in the room. There's a direct correlation between the number of particulates and the number of microorganisms present. So our physical monitoring is making sure that we are controlling the environment to reduce the risk of microorganisms being present in our clean room. We also have to make sure that we're monitoring our equipment. So essentially, when it comes to equipment, you want your equipment to be within certain parameters and to not deviate from that. They are set at certain parameters to reduce the risk of contamination either to the operator or to the product itself. We are always thinking of lowering the risk of microbial contamination to the product. Therefore, we work in things like laminar flow cabinets or isolator cabinets, where you can achieve a grade A environment, so a sterile environment. We need to be monitoring those and making sure that every day they are performing to the correct specification. We monitor the process. So our microbiological monitoring of the process can involve our sessional plates, our finger dabs in our grade A zone, but also we want to mimic the production process. As discussed before, we cannot test our final samples all the time, especially in a Section 10 unit. Therefore, we have to come up with an alternative method that will provide us assurance that our production process is lowering the risk of contamination by microorganisms. Therefore, we can do a couple of different ways of doing it. We have end of session broth fills or sterility testing. So what they do is you build a process that mimics how you would produce an aseptically prepared product. You would substitute the live product for something such as nutrient broth, and you would manipulate that broth, and that broth promotes the growth of microorganisms if there are any present, and will help provide assurance that our technique and our process of producing prepared products is of low risk of microbial contamination. We also need to monitor the personnel because, as mentioned, people going into the clean room is the biggest source of contamination, both for non-viable and viable particulates. So we have a very robust microbiological monitoring schedule. This is to make sure that we are constantly reviewing the performance and compliance of the personnel in the clean room. It's really important that we have a standard of compliance that is met by all personnel. So we have many ways of monitoring people in the clean room. We have their gowning technique, we have their aseptic technique, so how they make, their transfer technique, even down to the hand washing technique. We monitor all these things to give us an idea of our local microbial flora, and also it's a training aid. We help teach people how to behave in a clean room because aseptic technique and etiquette is really important to reduce the risk of microbial contamination, and also to give us assurance that they are able to perform these tasks adequately, lowering the risk. We can also look at disinfectant efficacy. So as mentioned, we do microbiological monitoring of the clean room to check that our cleaning process is adequate. We also need to make sure that our cleaning agents are adequate because, as we know from methicillin resistant Staph aureus, MRSA, microorganisms can evolve and adapt, so we need to make sure that our disinfectant, our cleaning agent, is still efficacious and performing the job as expected, and there's no upward trends in our local microbial flora. We could also consider testing our product. So as we mentioned, we can't test our final product at every stage because we have to take that straight to the patient for administration. However, we could consider sending off products that have not been used, so returns, waste products. We could send them off for microbial growth promotion testing, to see if contamination has been introduced. And that is something that at East Kent we're starting to develop a schedule whereby if we get returns, we would consider sending off to check that it is aseptically prepared and there's no microorganisms present. So when it comes to microbiological monitoring of the environment, we have random methods and we have organised methods. So our random methods are our settle plates, our passive air samples. So that's where you're laying out a plate and seeing what falls onto it. So it is largely based on whatever happens to be floating above the surface of the agar at the given time. We have contact plates, so that is random sampling of surfaces. We have swabs, and we have finger dabs. So they are random methods of sampling. Our organised methods of sampling would be active air monitoring using air samplers. So there's a list of air samplers here. You may be familiar with some of them. In my units, we use the SAS air sampler and the Merck, but I do know other units that use the Biotest, for example. So let's take a look at our sampling methods. First of all, we've got settle plates. So these are Petri dishes poured with solid media known as agar. The agar that we generally use in our clean room environments in the NHS aseptic units is TSA and SDA or SAB, so tryptone soy agar or saborodextrose agar. The reason we use these two is they are very broad spectrum agars. Our TSA is a broad spectrum nutrient agar that will generally grow most organisms. It does not inhibit or promote the growth of any specific organisms. Generally speaking, everything will grow. Our SDA promotes the growth of fungi and also yeasts, so our yeasts and molds. It will inhibit the growth of bacteria. So yeasts and molds generally grow slower than bacterial growth. So you will often find on a plate that is contaminated with a lot of bacterial organisms, the molds and yeast do not have the opportunity to proliferate, and they can be more difficult to identify and see them growing up because they're slower growing. So growing on a medium such as SDA kind of inhibits the growth of bacteria to allow for other slower growing organisms to proliferate. And there's loads of different types of agar out in the world. There's specific agars that will only grow one type of organism. So if you were looking for a specific organism, you can actually buy medium that only has nutrients in it that will promote the growth of that organism and inhibit the growth of any others. When we put settle plates out, a settle plate is you remove the lid from the agar plate and you allow a passive air sample. So you sit the plate out and you see what falls onto it. We have a maximum time limit of 4 hours for that. It used to be in 1981, the Parenteral Drug Association recommended only 30 minutes for plate exposure, but more recently other guidelines have increased that to a 4-hour recommendation. That's because 30 minutes probably isn't long enough to get a great sample. So if we expose it for a longer period of time, we increase the sensitivity of the method. However, it's been capped at 4 hours for, we didn't want to reduce the recovery due to desiccation of medium. So as you can see here, if you work with 4 hours, you're increasing the likelihood, especially in equipment which is designed to extract air from it, for example, isolators or push air over the top of the surface, the risk of the medium drying out is significantly increased. Therefore, the maximum time we can expose our plates is for 4 hours to reduce that desiccation, because if you desiccate the nutrient agar, it inhibits the growth of bacteria. So conversely, 30 minutes probably wasn't long enough. 4 hours, you wouldn't want to go above that because you could inhibit the media in terms of recovery of bacteria because they need that moisture. So settle plates monitor airborne contamination and relies on floating viable particles falling onto the plate. The plates are irradiated, they are sterile, so they're terminally sterilised. You make up the media, you pour it into the plates, and then they're sterilised in their packaging. We can have issues because they've been terminally sterilised. There are issues with condensation on the plates or cracking, damage to the plates, which is why there is a specific way of storing your agar, which is agar face up and your lid is at the base, because if there's any condensation on your lid and that is contaminated, that condensation can actually run onto your plate and cause a false positive result. If you notice condensation on your plates, you should always check with your QA lead or your production manager to make sure that there's no that the product's okay and safe to use. but you will generally find there will be condensation on your plates, especially after incubation. Another method of monitoring is contact plates. So these are convex. They have agar in them that have a convex surface, and that is essentially just so you can make effective contact with the surface that you are applying and testing. So they are generally smaller surface areas, so that you have 90mm plates for your settles. You have 55mm plates for your contact samples. They will monitor surface contamination. So with our contact plates, we are generally making sure that the cleaning of that surface is sufficient. Normally done in designated areas around the clean room, which will be decided as part of your validation process. And you need a minimum contact period of 15 seconds. That's so that the microorganisms have an opportunity to adhere to the agar surface. The problems with contact plates is leaving a residue behind. If you forget to wipe that surface with an IMS spray and wipe, you could leave agar residue on the surface that you've just done a contact sample. That is detrimental because it then provides a lovely area for microorganisms to adhere and proliferate because you've left some of that residue behind. Another problem with contact plates is they are very delicate, and if you press too hard, you rupture that agar surface. So do not press too hard, very gentle. Just make sure you're adhering to the surface but not pressing too hard. They're also irradiated, so the plates come in irradiated packaging, and you need to store them the same way as I said with settle plates. They need to be at room temperature, agar face up and lids face down where you can. Swabs. As a microbiologist, these are my least favoured method of monitoring, if I'm honest. So you have a cotton swab moistened with sterile water or media. Avoid saline or peptone water because they can impair the proliferation of microorganisms in themselves by the nature of what they are. So you kind of want sterile water for injection. So swabs are for reaching those hard to reach places, so places that you would find difficult to clean or places that sediment can collect, so places that microorganisms might adhere to and then be able to proliferate, so corners, crevices, awkward areas, things that are difficult for operators to reach. So swabs are for reaching those areas and making sure that they are still maintaining a certain level of cleanliness. We take a swab by dipping it, moistening the tip, rubbing along the surface that we are sampling, and then drawing it across a settle plate and incubating it. The issues with swabs is that the transfer of organisms onto the swab and then onto the plate, there's no real data to show that that's effective. You need to have skill to do that, so you need to know how to sufficiently twist the swab tip to make sure that the entire surface is coming into contact with your agar. It's very difficult because a swab should be of 10 centimeters squared, which is considered the equivalent of a contact plate sample. However, without a template, or if you're going along an edge or along a crevice, it's very difficult to quantify 10 centimeters squared in practice. And as I mentioned, the number of organisms recovered by the swab method is significantly less than with contact plates. So swabs are encouraged, but they are not my favourite. So active air sampling, moving away from our random sampling, is a more accurate method of sampling. It's based on air being drawn in over an exposed agar surface. So you draw in 1 cubic metre of air, and any microorganisms that are in that air sample will be deposited on the agar surface. So when you take an active air sample, just after you've done it, you can actually see dimples on the agar surface where air has been forced onto that surface. In my unit, our air sampler uses 90mm settle plates. However, you can use agar strips, you can use contact samples, so it depends on the piece of equipment you've got. So moving on to, that's all the environmental microbiological monitoring. We also have to monitor our personnel and our process. So as I mentioned before, we have to have a gowning monitoring schedule, a hand washing monitoring schedule. We have to monitor the aseptic technique of each operator, their transfer process, so how effective they are at sanitizing a item to transfer into the work zone, and also cleaning validation, so testing the efficacy of the cleaning technique of the operator. As part of the monitoring process during production, we do finger dabs as well as the settle plates. So our finger dabs is taken by gently pressing the surface of our gloves onto an exposed agar plate. This is the same for a hand wash validation. You perform the same thing. Many interpretations of how you perform a hand wash validation. You essentially are demonstrating that an operator can go from having contaminated hands to non-contaminated hands via the correct techniques of hand washing and gloving, etc. Contact plates are used for our gowning validations. So if we are looking at how our operators gown up, you will generally take contact samples of where it is most likely that microbial contamination will proliferate. So where you've done up your zip, you would probably do a contact near your zipper, around your wrists where it has contact potentially with your skin. And also on the area of the suit. If you're using a laminar flow cabinet, you want to make sure that you're validating the area of the suit that is nearest to the airflow. This is done, all of these are done periodically, and we generally do gowning validations and hand wash validations on an annual basis. Our transfer process has to be every 6 months. We also have the broth validations. Again, that's performed every 6 months. Universal operator broth test. So this is testing the efficacy of the production process, but also the operator aseptic technique. So this will generally be by manipulation of broth to simulate a production process, but not using live product. Then that broth will be incubated and any growth is considered a fail. Good monitoring practices. So a well-designed and executed monitoring plan is essential. Sampling must occur at the same location at the same time of day. So you need to think about where you put the plates. This is really current. We need to be validating where we put our plates. They need to be relevant to our production process, to our equipment, to our personnel flow, to our workflow. So putting a plate for sampling in a corner of a room that never gets any production or any workflow probably wouldn't give us a representative sample of our process. Settle plates must be carefully placed so that they represent meaningful results, as I just said, and the results should be reviewed regularly with a view to changing locations if necessary. So we are always looking at our trend data, so what we are recovering from our clean room, and if we feel that we need to validate moving the locations, adding locations, removing locations if we are doing too many and it's not giving us meaningful results, that should be under constant review. So think about where you put the plates. Here's a diagram of a laminar flow and an isolator cabinet. So in our laminar flow, we have a plate here in the back corner. So our air flows from the grill at the back. So our cleanest area is at the back moving forward. Why wouldn't we want it there? Does that really represent our work zone? It doesn't. It's sat right next to the filter. It's got lovely clean air flowing over it, and it's not really near where we are going to be completing the production process. So here's our work. This is where our work zone is, our critical work zone. If we put a plate there, that would be slightly more representative of our working process. However, the actual work in front of it could impair the airflow. Therefore, that settle plate may be rendered not effective because the airflow is impaired by the work in front of it. Also, you wouldn't want it there because that is actually an obstruction to you trying to perform your production process. So you need to think about airflow, but you also need to think about not getting in the way of what you're trying to do and perhaps increasing the risk of problems with that product. So this looks like a better location. It's more central to the laminar flow cabinet, so it's not right near the back where the cleanest part is. It's not in obstruction to your work process, but it's alongside it. It's not impaired by any obstructions. So that's a better representative. So the plates need to be exposed at the same locations each time. I mentioned that before. That's decided during commissioning. So you need to validate this, as I mentioned, based on your airflow and your work patterns. So this will include your point of fill. So in the isolator cabinet here, this is the back left again. Not a great place, doesn't represent our working zone very well. It's out of the way, it's great for the operator as it's unlikely to ever be contaminated because it's not really representative of where we're working. Again, this isn't a great place to put it just because it is obstructing the ability to work efficiently, and also you need to consider your airflows. If that is being impaired by the work zone, you may not get all your contaminants flowing over the surface of that plate. So again, we want that plate to be sort of adjacent to our work zone in a representative location that doesn't impair our processing. And we want one in the hatch, our support hatches. In my trust, we do it sessionally just to provide us that extra assurance that our transfer technique is being effective. Here's a table of how frequently you should be monitoring on a microbiological basis depending on the sample type. So your finger dabs need to be every session in your critical zone. Your settle plates for your critical zone, again on a sessional basis. So every time you are in production, you need to make sure you have a set of finger dabs and a set of settle plates for your production. In the clean room itself, so the supporting controlled area, weekly settle plates are sufficient just to give us assurance that on a weekly basis there's no trends, no upward trends in what's going on, and it also provides us some data around that background microorganism, the flora that we have in our clean room. So our contact samples, our surface samples, should be done on a weekly basis as well. This is to be assured that the clean room is being cleaned every week, so they're not just cleaning on a monthly basis, they're cleaning every day, every week, and that the cleaning is effective. Active air samples, we have a slightly wider range on that. We can test quarterly as a minimum requirement. A lot of units decide to test more frequently. That's so they get some background data about seasonal trends, about trends when production levels fluctuate. So in my unit, we tend to perform a monthly monitoring routine. However, you can go as frequently as weekly. If we identified a problem, we would probably increase the number of air samples just to make sure we've got that environment under control. So to give us some assurance that what we do in response to any trends is working. Swabs, it says here to complete some swabs weekly. A routine, you need to decide where you're going to swab, so you need to have a good swabbing process and a clear schedule of where you're going to swab. So take a look around your clean room, find corners if there are any, undersides of trolleys, bits of equipment that have ledges. We want to identify those difficult to reach areas and swab them. And all of this monitoring is generally done on TSA. Of course, for yeasts and moulds, we kind of want to introduce SDA monitoring at various points. So that can range from every session to quarterly in the critical zone, or weekly to quarterly in the clean room. So dependent on the size of your clean room, the processing you're undertaking will influence how frequently, and also if you have a clean room that is prone to proliferation of moulds. So I know my unit, for example, in the summer will proliferate moulds, and generally in the winter we won't find any, but over the warmer months we will find that we recover more moulds. So you need to have an effective SDA sampling just to give us more assurance that we are also monitoring those yeasts and moulds specifically on a regular basis. This is taken straight from QAPS and the Orange Guide, the MHRA Orange Guide. This is the limits for your monitoring. So in your grade A, you don't want any growth. In the MHRA Annex 1, there's been some further clarity around your grade A. The less than 1 has become 0. Obviously you can see, dependent on the grade, gives us those limits for recovery of colony forming units. So colony forming units, they are taken to have been produced by one microorganism, and as that microorganism multiplies, it becomes a colony forming unit that we can see with the naked eye. Obviously when you originally take your sample, you won't see anything on the plate because microorganisms are too small to be seen by the naked eye. So we assume each colony that has grown up after incubation has formed from one microorganism. However, that is not necessarily the case. Our finger dabs, they are expected, and they are expected on a sessional basis at the end of each working session. So they are to monitor your gloves when you have been producing aseptically prepared products. So you want to test both gloves and gently dab each fingerprint onto a TSA plate. Problem with finger dabs is obviously if you press too hard, you rupture the surface of the agar. You don't want to leave a residue behind on your gloved fingers and then carry on producing, because it provides, again, a lovely surface area for microorganisms to proliferate. So you want to make sure that after you've taken your finger dabs, you then clean your gloves or change them, depending on your processes. And by the nature of your finger dabs, if you have been working in an isolator or a laminar flow cabinet with your gloves on, if you've been working with a cytotoxic, or if you've been working with cleaning agents between your products, there is likely to be the presence of inhibiting residues on those fingers. So the meaningfulness of the results could be challenged, because if you have cytotoxics on your finger dabs, it could impair the growth of microorganisms. So you need to be aware that there could be inhibiting materials on fingers on your gloves. This is an ongoing discussion. Who monitors in your clean rooms? Some units are fortunate enough to have an independent quality assurance or quality control team. However, some have to perform the monitoring themselves. So the production team have to do their own monitoring. I'm QA and QC. I've always worked separately to the production units. My argument is, if you have an independent person or team to be able to perform your monitoring for you, that would be ideal. The reason being is you want to remove that conflict of interest. Obviously, if I'm an operator and I'm making products on a daily basis, I don't want my microbiological monitoring to fail. I don't want it to appear like I have less than adequate aseptic technique. So just having that testing performed by a separate staffing group, that provides us that assurance that the conflict of interest is removed. Also, operators are generally concerned with making sure that they are involved in the production process. It's a time-consuming process. If someone else can perform it for you, bonus, you get more time to make, and someone else can do the micro monitoring for you. Incubation times is something to consider. There is a varying range of advice about incubation times. The minimum is generally around 5 days. That is the sort of minimum time that it takes for the slower growing organisms to start proliferating to a point where we can see them. You want to consider your temperatures for incubation as well. That also affects how long you incubate for. You generally incubate, I like to employ a dual incubation. So we have the plates are incubated both at room temperature and at 30 to 35. So as it mentions here, your 20 to 25, your room temperature is for your environmental isolates. So waterborne organisms can grow at this temperature. Your fungi, your yeasts, environmental isolates will generally proliferate at this temperature. So I favour incubating the plates at this temperature primarily, and then moving to a warmer temperature. So the warmer temperature allows for the proliferation generally of bacteria, largely because they like to live on us, and our sort of external body temperature is around 30 to 35 degrees. So that mimics sort of the environment that organisms that are being brought in by personnel would be accustomed to. So we have a dual temperature incubation, but if you're just looking for yeast and molds, you would just incubate at 20 to 25 because that's their preferential temperature. Bacteria, generally speaking, will grow at room temperature or nearer body temperature. We incubate our plates for less time than our broth. That is because our plates firstly are prone to desiccation, so they will dry out as you incubate them. The longer you incubate them, the thinner they become, where the moisture is being drawn out, and the less likely bacteria can proliferate on them. So we do limit the number of days that we incubate. Our broths we leave to incubate for a bit longer. This is because sometimes organisms can be slow growing in broth, and it's just because of the moisture content, broths can tolerate longer incubation times. So our interpretation of our results, when we look at our results, we investigate, so we have an alert level which is a threshold where we need to investigate what's going on. So we have a routine level of organisms that we would expect to see in our clean rooms, and that should be local and decided by your group. And if it exceeds that, we are concerned that there may be an issue. We would investigate that. It's a warning limit for us. However, our action limit is our absolute no, you should not be reaching that level of organisms in the grade of controlled area that you are trying to maintain. Therefore, we would probably need to stop and look at our processes. Do we need to implement a clean? We need to do a root cause analysis. How has that contamination got in there? What can we do to stop it getting in there again? And again, lots of monitoring, probably an increased monitoring schedule in response to that as well. So when we have a failure, we need to identify the organism. So if our recovery exceeds that of the action limit, we need to know what we are recovering to try and understand where that has been sourced from. So you can, from different types of organisms, kind of understand where they have been sourced from. For example, Bacillus species and Aspergillus are generally airborne. Pseudomonas will come from water. Staph aureus or Epidermidis come from people, originate on people's skin, in their nasal passages, mucous membranes. And again, Micrococcus luteus and Lilae, which are the top two organisms recovered from clean rooms, they will be, generally speaking, brought in by the personnel. It's very important you trend your results. So not only doing the testing and reading the plates after incubation, it's really important that you trend those results and share your findings with the team to help them understand why it's important they clean, why it's important they always implement good aseptic technique, why it's important we do hand wash validations, etc. Any deviations we should document, and we should take action in response to that. So we should be using our quality management system for that. So documenting all our non-conformances and making sure that we've investigated and closed them out in a timely manner. So we need to also consider other microbiological monitoring. I've already mentioned broth simulation, so our universal operator broth test. That assesses both the production process but also the operator technique. So it gives us a personal profile of each member of personnel. Practices should be consistent across the board. The process will mimic a live production process using the maximum number or a varied number of manipulations, and a varied number we should rotate the final storage container and the number of withdrawals, etc. So it gives us a good overview of our production process. It should be worst case scenario to demonstrate that we can perform our processes aseptically without contamination. We also have our transfer validations. So this is to challenge the technique of our transfer sanitization process to demonstrate that we can take a non-sterile product prior to sanitization. We will take a contact sample and then we will repeat the sampling after the transfer sanitization steps, and we should be able to demonstrate that we have reduced or eliminated microbial contamination from the surface. So always remember, it's always drilled into me, occlusions, do not neglect the occlusions and any folds in your consumables. We also should have a sterility testing rota, so sterility samples should be produced and retained and then sent off for sterility testing. This is another, we sort of moved away from sterility testing slightly, but that will be coming back into focus. It should be a combined monitoring schedule that is complements the end of session broth fills. With sterility testing, there's a discussion whether we should use unused products, so waste or returns, or mock products. We used to fill saline bags, literally withdrawals of saline, and send that product after we've manipulated it off for sterility testing. The problem with sending saline for sterility testing is the nature of saline is it could actually inhibit any organisms that have been introduced. Is it representative of a true sample? It's questionable depending on what your diluent is. It doesn't represent any of those that are made in glucose. So unused product would be preferential, but again, the nature of the product, would it promote the growth of any organisms? Would it be meaningful data? So you need to consider that when you're building your sterility testing regime. We need to monitor our drains and sinks. So any drains and sinks used, we shouldn't have any water sources in our clean room directly, but things for hand washing, etc., or equipment cleaning outside of the clean room, we should monitor those to make sure they are of a level that is acceptable. You don't want to be washing your hands prior to going into the clean room with water that is highly contaminated, because it actually increases the risk that you're then going to transfer contamination into that clean room. So we have a limit of less than 100 colony forming units per mil in hand wash water. We also want to make sure that our cleaning equipment is monitored, because if you have a bucket that you are making up cleaning fluids in and it's regularly contaminated, you're actually just spreading the dirt around the clean room. So you need to make sure that you're regularly swabbing, monitoring your disinfectant bucket. And any hand dryers you've got. I haven't seen many units that still have hand dryers installed, because it blows dirty air around the area that it's located. But if you have hand dryers, you should be monitoring those as well for microbial recovery. So contamination control strategy. This is quite a new topic, and it's a very current topic to be discussing. All units should be locally assessing the risks of contamination via all routes into your clean room. So you're looking at your final product and working your way back. It's usually performed by process mapping the entry of product, materials, personnel and equipment, etc. Once mapped, the areas of risk can be highlighted and mitigating actions put into place to proactively lower the risk of contamination. So what this CCS is for is to identify where you think contamination can come from and prevent it, reduce it, without having to have a failure to then work your way back. This is a document. It should be quite an informed document, and it should influence validation master plans and sampling plans. And will directly link to your quality management system, and it may involve the initiation of a change control process if you identify a risk that needs mitigating. There is a more recent requirement to have the CCS documented. It should be regularly reviewed and reassessed as your processes are regularly changing and need updating. This CCS should be formed using a multidisciplinary team, so you have lots of different approaches to identify all the risks. So the purpose of the contamination control strategy is to proactively lower the risk of contamination ahead of contamination occurring. So in summary, what are the different methods of microbial monitoring? Well, I've talked a lot, and that was a lot of information, but I hope it was useful. We have settle plates, so passive air samples, contact plates, contacting the surface that we wish to monitor. We have swabs for those hard to reach places, and we have active air sampling, which actively draws in a volume of air. We also have our broth tests or simulations to monitor our production process, our transfer process, and all these different methods of monitoring are really vital in providing assurance that our final product is of the expected quality that we require. So reducing and minimising that risk of microbial contamination. It's important that we look at all of these results in a holistic approach, so they all influence each other. They aren't independent of each other. It is providing us an overview of our clean room and our processes of transferring products in and out and consumables. And it's really important that we trend all these results and monitor any changes, variations or anomalies to provide assurance that our clean room is performing at the level that we expect. So that's all I have to say about microbiological monitoring. If you have any questions, please do ask, and I will endeavour to get back to you on a remote level. Thank you very much for your time.